In this lecture, we will talk about a very commonly encountered unit in RF and microwave, which is decibel unit. And then we will see the amplifier nonlinearity and its undesired effect on the output. So first, we will study what is decibel unit. So this unit is used to convert large quantities encountered in electrical engineering into small numbers. Say, for example, if we have X as a large and unitless quantity, and if we want to convert it into a smaller number, then what we can do is we can take the help of log function, which we know that compresses or reduces a large number into a small number. So we can take its log to base 10. Now this number is going to be small and it will remain, of course, unitless. So although we started our discussion with a large number, but we know that log of even small number can be taken. So whatever we are going to talk about is valid for even small number x. So we say that this quantity x in logarithmic scale, which is called Bell scale, is converted by finding log of x to base 10. And now we say that x has been expressed in Bell unit or designated by capital letter B, and this is going to be equal to log of x to base 10. And this unit Bell is named after Alexander Graham Bell, who we know invented the telephone. In electrical engineering, there are many situations where we encountered uh, unitless quantities. For example, power gain of an amplifier. Which is designated as capital G, and this will be equal to output power divided by input power, and this quantity is clearly a unitless quantity because both the powers are going to be in same unit of watt. Typically this will be large number, say for example 10 or 20, or in some cases few hundreds. So we would like to express this in Bell unit. So we say that G in Bell is found out as log of PO by PI to base 10, or G in Bell is log PO by PI base 10. Now if G is less than 10, then we know that this is going to be a fraction. So for G less than 10, G in Bell is going to be less than 1, and this is going to be fraction. And there will be many scenarios where this will actually happen. So to avoid dealing with fraction number, what is done is that we create a smaller unit compared with the bell. So we go for smaller bell unit. So this is similar to talking about centimeter, which is 100 times smaller compared with a meter. So 1 centi is equivalent to 100. Similarly, millimeter is equivalent to 1000 of a meter. So for meter, centimeter, millimeter are quite frequently used. But even for meter, we can talk about unit or scale, which is 1/10 of meter. In that case, we have deci. 1 deci is equivalent to 1/10 of whatever unit we are talking about. So for example, 1 decimeter is going to be 1/10 of meter. So same uh, idea can be used with bell also. So for example, 1 decibel is equal to 1/10 of bell, and in short, this is designated as dB. For example, here also this can be written as dm, decimeter. So we say that 1 dB is equivalent to 1/10 of bell. So recall that this is the unit that we always encounter in electrical engineering. So now if we have something represented in bell, then how do we convert it into decibel? So for example, if X is in bell as X bell, then we know that this can be written as 10 into 1/10 bell. So here, these two can be clubbed together and these two can be clubbed together. So what we will get is 10x, and from here we know that 1/10 of bell is dB. So we see that x in bell is equivalent to 10x in dB, or log x 10, which is in bell, is equal to 10 log x 10 dB. So this is how we find out the decibel for any given physical quantity x. Now we started this discussion for quantity x, which is unitless, for example, power gain. But we would also like to uh, represent quantities with unit in logarithmic scale. Say, for example, power itself, or the input power to the amplifier, or the output power to amplifier. So how do we represent quantities with unit? Unit in decibel. Say, for example, we have power in watt. So we have P watt of power, and we want to express this in dB scale. So here we have two entities. One is this power. This is going to be a number, for example, 5 watts. and then we have this unit. So what we do is we take two steps. First is convert power, the number, in dB by finding out 10 log of P. And then to convey that it has unit, this quantity is not unitless, we write the unit of this quantity next to it. Next to dB. So P gets converted to 10 log P. Now this is in dB, but this is valid when P is having no unit. But since we have P watt of power, so what we do is we write W next to it. That means here. So P watt is equivalent to 10 log P of 10 dBW. So this conveys the unit of quantity which has been converted into decibel scale, and this is the number corresponding to conversion. Similarly, say for example, if we have P milliwatt, then how do we convert it into dB? We simply take 10 log of P to base 10, of course, dB. So this becomes P number into dB, and since it has unit milliwatt, so we write dBmW. So this milliwatt of power is very often encountered in RF and microwave domain. So this is going to be the most widely encountered unit. So that is what we do is we drop this W and we retain only M. So we say that we have 10 log P dB M. So dBm is shortened form for dBmW. So now let us take example of 5 watt of power. So here we have 5 watt. So we convert first 5 into dBm, and then we write not dBm but actually dBW. So here what we are going to get is 7 dBW. So this 5 watt is equivalent to 7 dBW. But now suppose we want to express the same 5 watt into dBm. So first we convert this into milliwatt. Now once we have converted it into milliwatt, what we are going to do is we convert 5000 into dB. So this becomes dB, and since unit is milliwatt, so we retain this unit milliwatt here, and this becomes 37 dB MW, or in short 37 dB M. So this is the final value of 5 watt in dBm scale. Now this scenario that we have to deal with power uh, appears in the formula of the gain. So we know that gain G is equal to PO by P in. And here the output power and the input power, they could be both in watt, or they can also be measured or specified in milliwatt or microwatt also. So now if we convert this into dBm or gain into dB, so what we get here is 10 log G equal to 10 log PO by PI. Now this can be converted into difference of two quantities. So 10 log PO minus 10 log PI. So this is gain in dB. But here we know that this output power and the input power, they could be either in watt or milliwatt, as we saw here. So then now we have to see that how to represent these quantities in dB so that their unit also gets conveyed. So if PO is in watt, so then we can simply write PO dB W minus P in dB W. That means both are in watt. Or if these quantities are in milliwatt, then we could have written as PO dBm minus PI dBm. Note that on the left side, we always have gain in dB, but on right hand side, the actual unit of power will vary depending upon what was the unit in which power has been specified. Similarly, one can have PO in dB microwatt and PI also in dB microwatt, and the gain remains in dB. So it can appear very surprising that when we are subtracting powers in dBm or dB microwatt, their difference is no longer in dBm or dB microwatt, rather it is in dB. And this should not come as a surprise because here the quantity, they are actually unitless, and we are dealing with ratio which gets converted into subtraction in the logarithmic scale. So now we'd like to see what will be their plot. That means plot of, say, this equation 1 and this equation 3. Let us call this as equation 2 and this as equation 4. So what will be the plot of equation 1 and say equation 4 or 3? 4 and 3, they are going to be similar. So from equation 1, what we find is that output power is going to be G into Pi. So here what we have is Pi on x-axis, PO on y-axis in same unit, and we have equation of a straight line passing through origin with a slope equal to G. However, if we see equation, say 3 or 4, for example 4, so here what we see is we again have output power, the equation of straight line, but in this case you can see that slope is no longer G, rather it is equal to 1. So here we have input power in dBm and output power in dBm, but now we have a straight line not passing through origin, rather passing through this number on y-axis and with slope equal to 1. So its slope is 1 and it is passing from G dB on y-axis. And this equation that we have written here will be helpful when we are dealing with amplifier. Say for example, if we have an amplifier here which is being fed with say -7 dBm of power, and it has a gain equal to 12 dB. So question is how much of output power we get. So output power we know that is equal to sum of input power in dBm and gain in dB. So this output power is -7 plus 12. And so here we won't have to worry about the unit. Actually, this is going to be in dBm and this is going to be in dB. Yet we will simply add them and try to get the number. So this is going to be 5 and this 5 unit is going to be dBm. And this will be slightly more than 3 milliwatts of power. And this 7 minus 7 is equal to 0.2 milliwatt power. So here we interpreted dBm as dB of power, which is in milliwatt. But there's another interpretation for this dBm. We will see that also. So in this interpretation, we say that dBm of uh, power is actually dB of the power measured with respect to 1 milliwatt. So power measured or expressed with respect to 1 milliwatt. So what is meaning of this thing? Say for example, if we have P dBm of power, then this definition says that we take 10 log of P divided by 1 milliwatt. So here we see that this power is getting measured, expressed, or normalized or referenced with respect to this 1 milliwatt of power. And here the power, original power, this could be in any unit, either in watt or milliwatt or microwatt, it doesn't matter. So say for example, if P here is in watt, then what will happen is this is in watt. So how the calculation will go? So P is in watt and this milliwatt can be expressed as 1000 of watt. So here we say that now both the quantities are in watt and the ratio is going to be unitless. So we can now do the calculation as log of 1000 into P. And in this case, this quantity is unitless. And this will, of course, turn out to be 30 plus 10 log P. So here also what we have done is we have basically converted the P watt of power into a unitless quantity by normalizing or referencing or measuring it with respect to 1 milliwatt of power. Similarly, the interpretation of P dB microwatt would be that we have a power and that is being now normalized or referenced with respect to 1 microwatt of power. Now suppose we have a power which is already expressed in microwatt. and we want to express it in dB microwatt, then what will happen is then 10 log P microwatt divided by 1 microwatt. So in this case, we already have numerator and denominator in same unit. So calculation will be simpler. Simply 10 log P, and this will be in dB microwatt. So whether you go for this interpretation or the earlier one, that means this can be directly converted into 10 log of P, and you just write dB and this unit here. So both gives same result, and both are equivalent interpretation of dB microwatt or dBm or such units. Now we have been talking about power with unit. So question arises, how do we deal with voltage or current if they have unit? So we start with the equation for the gain, power gain. So we now want to know voltages in dB. How do we express these things? So we start with G as PO by PI. Now we will try to represent this output and input powers in terms of voltages. So for that, we will have to see the actual scenario a little bit more detail. Say for example, we have this voltage amplifier which has power gain is equal to G. So this is the model on the output side. It has output impedance of RO, open circuit voltage of VO, input resistance is equal to RE, and this is being fed by non-ideal source with internal resistance is equal to RS, and on the output side it is connected to load. Load experiences voltage VL and input resistance experiences voltage VI. So we will now convert this output power into voltages. So we know that this output power PO is equal to VL square divided by 2RL, where VL and VI and other voltages are peak amplitudes. Similarly, the input power is VI square divided by 2RI. So we can see that gain G is going to be equal to VL square divided by 2RL into 2RI divided by VI square. Now here we can separate out voltages and resistors. So VL square by VI square into RI divided by RL. And we know that, okay, so now if we want to convert this into dB scale, G in dB, so we take 10 log of G, and this will give rise to 10 log of VL square by VI square dot RI by RL. And we know that for RF and microwave, these resistances, they are going to be equal and equal to 50 ohm. So this G in dB becomes equal to 10 log VL by VI whole square. and this becomes 20 log VL by VI. And here, all these voltages, they are going to be in same unit of either volts or millivolts or microvolt. So here we can see that they will always be unitless quantity, and this VL by VI, this is called voltage gain. So here we see that gain in dB is equal to 20 log VL minus 20 log VI. So now here we have a scenario which is similar to what we got for output power and input power. Gain when it was expressed in terms of these two quantities. So from here we can say that whatever may be the unit of VL, the same unit will be for VI. And then we can say that if say VL and VI both are in volts, then we can say that VL in dB volt minus VI also in dB volt. So by extension, we can say that we can represent or take the load and input voltages in millivolt also, or in microvolt. So once again, we see that we take the two voltages in same unit, do the subtraction, and what you will get is power gain in dB. Now this was for voltages. What about currents? So for currents also, we do the similar thing. That means suppose we have current I expressed in ampere. So this, when it is converted into dB scale or Bell scale, it will be written as I dB A. And this will be calculated as 20 log of I. Now if I were expressed in microampere, in that case we will write I dB micro A, and this will be simply equal to 20 log of I. Now if suppose we have I in ampere, but we want to represent it in dB MA, that means milliampere, then what we will have to do, we convert this into milliampere, so that becomes 1000 into I milli A. So now what we do, we find out the decibel for this thing and retain this unit. So this becomes 20 log 1000 I dB MA. So this was one interpretation. Second interpretation is also valid. So that says that you take 20 log of I, which was in ampere, divided by 1 milliampere. And this is going to be dB MA. So here also you can see that what we will get is same thing, I A divided by 10 raised to the minus 3 A dB MA. So in both the case, so we will end up with the same value. So this was about the dB scale. Now we will talk about the effects of non-linearity of an amplifier. So for ideal or linear amplifier, we have this scenario that if it is being fed by input voltage Vi and if the output voltage is Vo, then output voltage will be scaled up version of the input voltage by factor A. And we say that this is the voltage gain of the amplifier, and the plot of Vi and Vo is going to be a straight line with slope equal to A1 passing through origin. And we say that this is linear amplifier. This is the ideal scenario that never happens in real life. In reality, what happens is output is going to be a more complicated function of the input. In reality, the output is going to be like this. E1 Vi, this is the usual term that we want. Now there will be terms which will depend upon the second power of the input, third power of the input, so on and so forth. And this process will continue. And we say that amplifier is nonlinear because in this case, superposition principle will not hold true. Or plot of this is no longer going to be a straight line passing from the origin. But fortunately, in real life, all these coefficients, they are very small, and in most of the cases, they can be neglected. So now let us try to retain these two terms, additional terms, square and cubic terms, and neglect the fourth and higher order terms. And let us see that what happens to the output. So we approximate output as A1 Vi plus A2 Vi square plus A3 Vi cube. So here we are going to take input as A cos omega t, and now suppose we have an ideal amplifier, then what will be the scenario in frequency domain on the input side and the output side? So on the input side, we have a pure sinusoid at omega naught of amplitude A. So when this passes through ideal amplifier, on the output side, we will have A1A cos omega naught t. That means in the frequency domain, we will continue to see only one sinusoid of strength A1A. So in this case, frequency content of input and output both are same, and since this is amplifier, this is supposed to enhance or increase the amplitude, and that is what is getting done here. So we had A here, now we have A1A on the output side. So when we talk about nonlinear amplifier, so nonlinear amplifier will change both the aspects of the input signal. That means it will modify this frequency and of course the amplitude as well. So this will have effect on both non-linearity effect will be visible on both frequency, content of the output, and amplitude of the fundamental on the output side. So we will see that we will no longer have only a pure omega naught term, and the amplitude of the fundamental will no longer be purely A1 into A. So here we see that non-linearity effect effects are visible in both frequency domain and in the amplitude domain of the output. So in real life, very rarely we will have a signal which will be pure sinusoid. In fact, the actual signal is going to be a band of frequencies. So finding out the complete effect of nonlinearity on such signal is going to be a lot more difficult to analyze and to experimentally study also. So to simplify and still get the good idea of what effects are there on the frequency and amplitude of the output, we take two distinct cases for the input. So we take input in first case as a pure sinusoid. That means single sinusoid, and such inputs they are called one tone input. And in second scenario, we take situation a little bit closer to reality. That means we take two sinusoids and then study what will be the output. Such inputs are called two-tone inputs. So first we will study the effect on the frequency of the output for single sinusoid case. So we will analyze what is the frequency content of the output. And we will see that we will no longer have pure sinusoid on the output side. There will be many other undesired harmonics of the fundamental, and that will cause the distortion in the shape of the output. So this scenario leads to harmonic distortion. So we have our usual input A cos omega naught t, and this is being fed to amplifier whose output is A1A VI, A2 VI square plus A3 VI cube. Now we want to know what will be the output. So we substitute this input in this equation for each of the VI. So VO now becomes A1A cos omega naught t. So this is ideally we want. But now the remaining two terms, they are going to create issues. So these are the three terms. We will have to expand them to find out what will be the actual content of the output. So we expand this second order term and third order term. So the first one remains as it is, A1 A cos omega naught t. The second one, when expanded, this will give rise to A2 A square by 2 into 1 plus cos 2 omega naught t. And the third term, that will give rise to A3 A cube by 4 into cos 3 omega naught t plus 3 cos omega naught t. Now here we see that we have now a term here which is independent of time. So we will say that the DC gets created because of the second order term, which will not be present in the ideal case. So now when we segregate each of the terms, so we have now a DC here arising because of the second order term. And then we see that third order term, this leads to again a fundamental component. So this fundamental will combine with the expected fundamental and give rise different fundamental now. So that is going to be A1A plus 3 by 4 A3A cube cos omega naught t. Now the second order term that gives rise to a second harmonic. So here we have second harmonic A2A square by 2 cos 2 omega naught t. And third order term gives rise to third harmonic A3 A cube by 4 cos 3 omega naught t. So now if we see the output in frequency domain for this amplifier, so what we are feeding here is pure sinusoid at omega naught of strength A. This is Vi. But on output side, what we are going to get is our usual fundamental at omega naught. But in addition to this, we are now going to get multiple undesired components also. The first is going to be at DC, and then second is going to be at 2 omega naught, and there is going to be another one at 3 omega naught. So here, what we see is we have undesired frequency components, and in this case, the shape of the output is no longer going to be pure sinusoid. And this DC component is not very serious component, because this will simply give rise to shift in the output along the y-axis, either in positive direction or in the negative direction, depending upon the sign of this. But these harmonics, they will combine with the fundamental and change the shape from pure sinusoid. So they are going to be more serious. So one then can ask, is there any way of getting rid of these components? So fortunately, at least for the even order terms, there is a way of getting rid of their effect. So now let us consider a differential amplifier. Suppose instead of having a single-ended amplifier, we take a differential amplifier. So now we have our input splitted into Vi plus and Vi minus. Similarly, the output also splitted into Vo plus and Vo minus. So the actual input is Vi plus minus Vi minus, and the actual output is Vo plus minus Vo minus. Now, if we have this type of amplifier, then let us see that what will happen to the output for non-linear amplifier. So this is non-linear. And we will consider non-linearity up to third order. And here, this Vi plus is minus of Vi minus. And this will be A by 2 cos omega naught t. So now each of these Vi plus and Vi minus will get modified by the output expression. So Vo plus is going to be given by the cubic expression for Vi plus. That means A1 Vi plus A2 Vi plus square plus A3 Vi plus cube. And similarly, Vo minus is going to be A1 Vi minus plus A2 Vi minus square plus A3 Vi minus cube. Now, since the output is difference of these two, so Vo is Vo plus minus Vo minus, and this can be found out. So here we will get A1 Vi plus minus Vi minus plus A2 Vi plus square minus Vi minus square plus A3 Vi plus cube minus Vi minus cube. So we can substitute Vi in terms of Vi plus to see that what will be the output. So when we substitute this, we get A1 Vi plus Vi plus A2 Vi plus square minus Vi plus whole square plus A cube Vi plus cube minus Vi plus cube. So here we can see that this term is going to be 0. This will become equal to 0. So what we will be left with is only the first order term, which is 2 times V A1 Vi plus 2 times A3 Vi plus Q. So now we have an output which does not have any second order nonlinearity. So this implies there will be no DC term and there will be no second harmonic term also. By extension, if we were to include other higher order terms, for example, fourth, fifth, so on and so forth, so you can see that all the higher order terms, they will also get eliminated out. None of these will be present on the output side. So differential amplifier rejects the even order nonlinearity. So at least even order nonlinearity can be tackled to a great extent with the help of differential amplifiers. In the next lecture, we will see the effect of the nonlinearity on the amplitude of the output for single tone input.